So for the second talk in the session, we'll have Zahra Khatami from Louisiana State University, and she'll be talking about applying logistical regressions to parallel loops in HPX.
Hello. My name is Zahra. I'm working at Stellar Group at Louisiana State University, supervised by Dr. Kaiser. Today, I'm going to talk about our recent work, which is applying logistic regression model on HPX parallel loops. After giving a motivation of this work and just a brief description of the HPX framework, I will explain more details about our proposed methods for HPX current challenges, which is based on machine learning, and then we will go through the experimental result and conclusion. The parallel performance of most applications depends on loop level parallelism. Just imagine that we have an application that has thousands of loops. Parallelizing all of the loops within that application may not be the optimal approach for achieving desired scalability, because some of the loops cannot scale on more number of threads. So they have to kind of, I don't know, execute in parallel. Some of them should be executing sequential. The other is that there are lots of parameters such as chunk sizes that in most of the framework, there aren't any, that optimal approach or optimal techniques for assigning those parameters. So for assigning the execution paths, for example, sequential or parallel, and also setting the chunk sizes of the loop, both dynamic and static characteristics of the loops should be considered. Before going through the challenges in HPX, I think that most of you know what is HPX, but for the one who doesn't know, it's a parallel C++ runtime system. It enables fine-grained task parallelism, which is mostly result in having a better load balancing. It provides efficient, scalable parallelism by reducing slow factors, which are starvation due to poor utilization of resources, latencies due to the delay of accessing to remote resources, overhead of scheduling parallel tasks, and also waiting to accessing the shared resources. But how HPX overcomes these factors is I'm just showing the general picture that in the right-hand side, I'm showing the what's happening in parallelization in most of the conventional techniques, that there is a barrier after executing threads in parallel, and before going to the next step, there's a reduction function that all of the threads should stop, and then that before going through the next step, even if those threads result are not depend on each other. And how it's solved in HPX is because HPX techniques is based on future. Future is a computational result that is not known yet, but it will be known in a later time. So I'm just showing that two threads. The thread one in this, and at this time, it needs a result from other locality. But thread 2, because it doesn't depend on the result from the other thread, it will continue execution without waiting that thread to be, to get its result. And then when we ask the future to get the result, it will wait till it gets a result, and then this thread will be reactivated. So as you can see, there isn't any global barrier between two independent tasks in the parallel threads. But what are the current HPX challenges? Execution policy has been defined in HPX, and which specify execution restriction of the work item. It means that if the execution policy is sequential, it will run the application sequentially, and if it's parallel, so it will run it in parallel. But these execution policies should be manually selected by user. But user may not know what is the optimum execution policy for that loop. The other challenge is about the chunk size. Chunk size is determined with these two approaches in HPX, which is called by auto-partitioner, which is exposed by the HPX parallel algorithm, which automatically determine the chunk size at runtime by just some methods, but it has overhead, which that on some loops. The other thing is to passing a dynamic or a static chunk as execution policies parameter, but these chunk sizes should also be assigned manually by user, but user doesn't know what is the optimum chunk size for that loop. So the solution is that we want to automate these parameter selections by considering loop characteristics and implementing that in the learning model. Our main goal is to combining these three different fields together, machine learning, compiler, and runtime, for utilizing maximum resource availability. And the raw idea is that kind of we want compiler to extract a static information of the loop, and we want runtime to extract dynamic information of the loop, and we want them to feed this information into the learning model, and then learning model somehow tell runtime at a runtime system, tell the system that, okay, what is the execution path for that loop, or what is the chunk size for that loop. Our proposed method consists of 4 stages: designing learning model, special execution policies, feature extraction, and learning model implementation. For learning model, we choose logistic regression model because that was easy for implementing, and it resulted in very good accuracy. For determining execution policy, we implement binary logistic regression model to determine that if that loop should run in sequential or parallel, so that's binary. And for the chunk size, we chose a multinomial logistic regression model. So I'm not going through the logistic regression models. They're just some mathematical equation. I'm just going to tell that, okay, output of this binary logistic regression model is going to be 0 or 1. 0 is going to assign for sequentially, and 1 to assign execution policy to be parallel. And for the multinomial logistic regression model, it's going to find the efficient chunk size between these chunk size candidates, which is 1/1000, 100, 1/10, and half of the loop iteration. So far, we designed our learning model, and this learning model is designed offline, so it will not going to add any overhead at compile time or runtime. We collected enough data to cover our various application, but it's going to be extended more. And so after this step, we have weights of binary regression model, and we have weights of multinomial logistic regression model. So these weights should be considered with the feature that's going to be extracted from the loop. For the feature extraction, we define some flag for a client compiler that to kind of tell compiler that we want features from this loop to be extracted. So these flags, for the execution policy is parIF, and for the chunk size is the new execution policies parameter, which is adaptive chunk size. So I'm just showing two simple loop here. The first one is using parIF as execution policy within the for loop, and then it will it will execute lambda function in that range. And the second loop is a for each, which our policy can be sequential or parallel with a new execution policy parameter, which is adaptive chunk size. So whenever compiler sees these flags, sees these things, policies within the loop, it's kind of it will extract features, static features from these two loops. So what we did was to introduce a new Clang tool named for each call handler. So I'm just showing the that's just a small part. I think that was enough to understand that if the policy contains parif or adaptive chunk size, it will extract the feature and it will do something within that loop. But what kind of feature we extracted is about 11 features that is showing in this table. The first two are dynamic, and it's not going to be extracted with compiler at compile time. The compiler will that produce API for the runtime, for example, HPX number of thread instead of that feature value. And then these two dynamic feature will be, their values will be assigned during runtime. The rest of them are static, for example, number of total operation, float operation, comparison operation, and etc. And for avoiding overfitting, we implement a decision tree classification technique, which the first 6 features were selected as a feature that we want to be considered within learning model. For considering both features, the values beside weight values, we just define two function, which is sequential or parallel, which compute the cost function of the learning model by considering the features values and also retrieving the binary logistic regression model weights. And also for determining a chunk size, we define chunk size determination that it also computes the cost function of the multinomial logistic regression model by considering feature values and its weights. So far we could kind of combine these two fields together, but what about runtime? That was very easy. The sequential or parallel and chunk size determination, we modified the compiler a little bit that it will produce those functions within the loop automatically. So before compilation, I'm just showing you our first loop that we use parif and policy with adaptive chunk size within these loops. And after compilation, compiler will see the parif, so it will automatically change the code in if sequential or parallel by considering that extracted static or dynamic features. It will, if this is true, it will execute in sequential. If not, it will execute in parallel. And for the second loop, instead of instead of execution policy parameters, that's for assigning chunk size, it will it will compute the output of chunk size determination by considering those as extracted features, and then it will during runtime, so it will set and it will assign the efficient chunk size based on that. So we could combine these 3 fields together. And about that execution experimental result, we test our methods on with Clang compiler and with the latest version of HPX. I'm just showing you the experimental result, which is kind of there are lots of numbers here, but I highlighted the second test. So as you can see, we have 5 different test cases. It's kind of, imagine that we have 5 different applications. Each application has 4 different loops. So why we choose that? Because we wanted to show that some loops should be executed in parallel and some loops should be executed in sequential. I'm just focusing on the second test. So for example, for the first loop with different characteristics, for example, the number of iteration, total operation, float operation, our policy were determined with parallel on 8 threads, and the chunk size was determined to be 1/1000th of the loop iteration. Or for the second loop of this test case, it was determined to be executing sequential with 1/10th of the loop iteration. And about the time, as you can see, I mean here showing execution time versus number of versus the test cases. For the test case 2, this diagram shows, the blue diagram shows that if we execute all of the loops within the application sequentially. The orange one shows that if we execute all of the loops in parallel, and the green one shows that what is the execution policy determined, what is the best execution policy determined for that loop. So as you can see, in most cases, the green one was better than executing all of the loops in parallel. Or for the chunk sizes, the blue one shows to assigning all of the chunk sizes of all of the loops within the application to be 1/1000th of the loop iteration, and etc. I mean, that's just setting each chunk sizes for to be the chunk size candidates, and the green one shows the performance of method, which was, that improved by up to 60%. That was very interesting for us as well. And as a conclusion, I'm just showing that we could, combine these 3 different fields together by training learning model, by adding some new changes in HBX to support our proposed technique, and by adding new Clang tool just to to create our proposed method at runtime. And all of the source code can be found in our GitHub in the HBX ML. And if you have any question, you can join our IRC channel. Okay, that's it.
We have time for questions for the speaker.
This is sort of a small side note, but you're running a 32-bit version of Mint. Is there a particular reason for this choice, or was
no,
this
that was just my local.
Okay. All right. And what IRC server does one need to connect to?
A Stellar. Yeah.
You have your own IRC server? No, not the channel, the server. Is it like Freenet or FNet?
Yeah. I mean, that's IRC's kind of. It's Freenet, and you can join each channel, and our channel name is Stellar. Yeah.
Right, but yeah, there are different networks. So the question is basically which one of the.
I don't know. I mean, I can check.
Okay, nice.
But, yeah.
Because you wrote tooling specific for Clang, it should be fairly portable across C++ itself. So maybe have you tried looking at how this might be used in something like TBB, for example? Is this even feasibly portable to another task-based system?
I don't know about that. We chose Clang because it's we could use LLVM, and that it's interface to apply our that tool and apply our techniques to extracting and then modifying the loops. But I think each that framework that is compatible with Clang, and Clang can be used as its compiler. This new Clang tool can be used for that. So, yeah.
That adaptive size that the green line represents, what approximate fraction of sizes were those? Was it between 1,000 and 100?
Okay.
And
so,
how many cores was that result on? I missed that part too.
Oh, it's on 8 threads.
Okay.
And yeah. So each core also has 1 thread, so it's on 8 cores. So that for the second test, as you can see that the green one has better performance, has less execution time. And because in this table, I'm just showing the chunk size determined for each of the loops. That for each for the first loop, it was determined to be 1,000th of the iteration. For the
I see.
second and third, it was 1/10th, and yeah, that was kind of different chunks are determined for different loops, I can say, within this application.
And maybe something I didn't understand, so maybe something obvious, but once you say sequential, what's the meaning of chunk size?
Oh, okay, yeah. Yeah, if it's sequential, so it will not, set any chunk for that loop, yeah, yeah.
Okay.
Okay. Yeah. Well, that's because, I think that I get you. That for the chunk sizes, the policy that was used here was par. And for the, that's just execution that was par if. So in these cases, in these test cases, when we wanted to, it was, it was tested twice. That for the first one, just to use, to assign, to determine execution policy with our proposed method, and without assigning any chunk size. That by let HPX to automatically assign a chunk size. And for the second one, we use parallel as a execution policy, and just to determine that what is the chunk size for that loop. Yeah, that's what difference. That I should say, yeah, that's not very good table. The policy that was used here was par, and the chunk size that was used here was automatically assigned with HPX. Yeah.
So if you take a in parallel, then it will be.
Yes, yes.
Okay, let's give our speaker another round of applause. So we're now going to